Okay, we're in section 2.4, and we're going to be introducing magnetism and electromagnetism in this particular section. Magnetic and electromagnetic fields play important roles and are fundamental to electronic and electromechanical systems. Motors, generators, speakers, microphones, computer storage devices like hard drives, and many other devices are based upon magnetic, electromagnetic principles. Okay, magnetic fields. Here we have a picture of one. Surrounding all magnetic objects is an invisible but measurable field. Now notice that. Surrounding all magnetic objects, it is invisible, it is measurable. A magnetic field is a region around a magnet where another magnet would experience interaction, and it would be either attraction or repulsion. The fields are not objects, but invisible lines of force. And so here we see a bar magnet, and we see the magnetic flux lines that appear around this magnet. Magnetic flux. The lines around a magnet are called lines of flux or magnetic flux lines. Each flux line is elastic but continuous. Flux lines never touch or intersect each other. The unit of magnetic flux is the Weber, and 1 Weber is equal to 100,000 flux lines. And the symbol for magnetic flux is phi, and that's this letter right here, the Greek letter phi. Magnetic poles. The regions in a magnet where external flux lines are most concentrated are called poles of the magnet. The poles of the magnet will attempt to force the magnet to align with the Earth's magnetic fields. The north-seeking pole is referred to as the North Pole, and the south-seeking pole is referred to as the South Pole. Like magnetic poles repel one another, unlike poles will attract. And let's see if I have a little, here's a little JavaScript tutorial over in this particular site called Molecular Expressions. And here we see a bar magnet, and it's not energized, but you see all these metal filings here, and if I press the little on button here, you'll see that the magnetic field will cause those filings to align in a certain way, and so that's kind of cool, little interactive video there. Okay, so magnetic poles. Flux density. Flux density is the measure of how many flux lines appear in a certain area. The unit of measure for flux density is the Tesla, capital T. 1 Tesla corresponds to a flux density of 1 Weber per square meter. And remember, 1 Weber is equal to 100,000 flux lines, so a Tesla has to do with 100 flux lines per square meter if it's 1 Tesla. If it's more than 1, then we're going to have more Webers per square meter. The more Teslas, the stronger the magnetic field. Magnetic domains. Materials that can be magnetized have regions called magnetic domains. Each magnetic domain acts like a miniature bar magnet. The length of a domain is only a fraction of a millimeter. They are very, very small. It takes energy to rotate or change the orientation of magnetic domains. This energy loss is often evidenced as heat in electromagnetic devices. Figure 216 has a text picture of this, and it displays the magnetic domains, and it shows them as they occur randomly, and it shows them also when a current is induced through it, and all of the little magnetic domains, then they line up and orient themselves, be it north or south. Magnemotive force. Okay, magnemotive force, MMF, refers to the energy source that actually creates the flux. It is the magnetic equivalent of, remember we talked about this, EMF. Remember that was voltage, and this is MMF. So it is the magnetic equivalent to voltage. The symbol for magnemotive force is, and it's right here. The unit of measure is ampere turns. Okay, and that is amps times time. Then we have magnetizing force. Magnetizing force, uppercase H, also called magnetic field intensity, is closely related to the magnemotive force, but includes a physical dimension. The unit of measure for magnetizing force is ampere turns, notice, per meter. So in this case, the magnetizing force H equals amps times time divided by meters. Now, since H is the result of amps times the fractional value of Tm, so you'd have amps times time over meters, the larger, or the fractional value of Tm, the larger the m, okay, the larger the m, the smaller the h. Okay, the h would be over here. H equals this times this. So the larger the h, the larger the m in the meters, the smaller the h, and vice versa. H addresses the concentration of a magnetic field. So if the concentration is smaller, notice if this field is in a smaller area, then the H is going to increase. And that is the magnetizing force. Then we have the term reluctance. It is the magnetic equivalent of resistance. Reluctance opposes the passage of magnetic flux. A material with a higher reluctance will have less flux for a given magnetic force. The symbol for reluctance is, here we have this R, and the unit of measure is A times time per Weber. Okay, more magnetism terms and units. Ohm's law for magnetic circuits, and this is kind of an interesting way to look at it. Remember that the magnetic force is equivalent to EMF or volts, so this would be equivalent to E. Reluctance is equivalent to resistance, so that would be R. And magnetic flux is equivalent to current. So magnetism is very closely related to electricity, and you see here very graphically the relationship between current, voltage, and resistance as related to magnetic force, reluctance, and magnetic flux. Permeability is the ability of a material to pass magnetic flux. Its symbol is the Greek letter mu. It is easier to pass a magnetic field through a material with a higher permeability. So the higher the permeability, the easier it is to pass a magnetic field. Permeability in a magnetic field is similar to, guess what? Conductivity in an electrical circuit. Magnetic versus electromagnetic fields. Many electrical devices use temporary magnets for their operation. These magnets exhibit magnetic characteristics as long as they're under the influence of a magnetizing field. Temporary magnets generally rely on the flow of electrons through a conductor to create the magnetizing field. The direction of magnetic fields is determined by the direction of current flow in a conductor. So this is an important point. The direction of magnetic fields is determined by the direction of current flow in a conductor. So if we look at this particular demo over here, here we have a DC supply. This is supplying DC voltage, and here we have a conductor. And what we're looking at here is the direction of the magnetic field that is built as current flows through this particular conductor. And so here we have this DC supply. Notice the polarity. This is the negative side, this is the positive side, and as current flows through this device, notice the magnetic lines of flux are forming in this particular direction. Now, in this case, everything is the same except that the current has changed. The polarity has been changed here, and so now the negative side, rather than coming in through the bottom, now the negative is going through here, and the current is flowing the other direction. So now the current is flowing through the wire in this direction, and you'll notice that the magnetic field now has changed direction. The lines of flux are now moving in this direction. The left-hand rule is one way of remembering the information on the previous slide. The left hand on the wire below illustrates the left-hand rule for magnets. The thumb is pointing in the direction of electron flow. Remember, negative to positive. The fingers wrapped around the wire indicate the direction of the magnetic field. So what do we say? And this has got to be your left hand. If you do it with your right hand, it'll be wrong. So with your left hand, let's see, this is indicating current going this way in electron flow. So if we had let's say we have a battery here, and this is the positive terminal, this is the negative terminal, and we connected a wire kind of like this, we would have, here is the direction of current flow, and the direction of the magnetic field is going to be like this, in this particular direction. And that's referred to as the left-hand rule. And interactive tutorials on magnetism. Earlier in this presentation I showed you one of the slides concerning magnetic orientation. If you want to go to that site, the URL is right here. If I'm going to post this link on the class website, but if you just want to jot it down, there it is. Okay, in this particular lesson we looked at, we ended up looking at the left-hand rule. We looked at magnetic versus electromagnetic fields. We talked about permeability, and remember permeability was kind of similar to conductivity. Remember we talked about Siemens, which were the reciprocal of resistance, and permeability is very similar in concept to conductivity. We looked at the equivalent of Ohm's law in terms of magnetism. We talked about reluctance, and it is electrically the equivalent of resistance. We looked at, I went the wrong way. Okay, we looked at magnetizing force, which is the symbol H, and the important thing about magnetizing force is it brought in the factor of area, in this case meters, and so the smaller the area of the magnetizing force, the greater that force. Then we looked at magnemotive force, and this was just amps times time, and it was roughly equivalent to EMF. We looked at magnetic domains. I didn't have a picture online, but we do have a picture in your text. It's figure 216. Flux density is measured in a unit called the Tesla. And we looked at magnetic poles, magnetic flux, and we referred to magnetic flux in terms of the Weber. And we looked at magnetic fields, and that concludes 2.4.